So 14.7, part 1.
Oh, I didn't do that.
All right, so a reminder for cylindrical coordinates. X equals r cosine theta, y equals r sine theta, and z equals z. So often people say cylindrical coordinates are polar coordinates with z. So when we talked about polar coordinates, we approximated the area. Let me just sketch up a little picture here. We approximated the area in the plane when we were talking about polar coordinates, double integrals with polar coordinates in the plane. We approximated the area with this little, we call it a polar rectangle. So here was our region looked like this, and we said this was delta r sub I, and this angle was delta theta sub I, and the area of this little polar rectangle was the average radius, r sub I, and our arc length, I forgot one thing, our arc length is the average radius, r sub I, delta theta sub I, was the arc length. And the area is r sub I, why did I put two deltas in there? R sub I, delta theta sub I. The area was r sub I, delta r sub I, delta theta sub I. So what we're going to do is, if we have a region, if we have a solid region that where we can represent the region in the xy plane nicely in polar coordinates, we're going to use cylindrical coordinates. So we're going to project this little polar rectangle up vertically. So what we're talking about there is if we had our three-dimensional coordinate system, we have a kind of a little portion of a wedge shape, and we're going to approximate the volume of that little wedge shape. So we're coming out from the pole here, and we get this nice kind of portion of a wedge-shaped solid. And if we project this down into the xy plane, we get our region in polar coordinates. So, and there's our little region, our polar rectangle in the xy plane. The only thing we're adding here, the area of the base of this little piece, is the area of our region in the xy plane, this r sub I, average radius, delta r sub I, delta theta sub I. This dimension here is going to be delta z sub I. So we have this little polar rectangle in the xy plane, and we're adding this delta z sub I to this volume element. So our volume of this little wedge, cylindrical wedge, delta v sub I, is going to be our average radius, delta z sub I, delta r sub I, delta theta sub I. And if we sum the volumes of all these little volume elements over our region, we get the volume of the solid that we're talking about. We take the limit as that delta V sub I becomes smaller and smaller. So we're taking the smallest diagonal of these little pieces and let that shrink down smaller and smaller. We get our definition of a triple integral. So we're going to sum these, take the limit as delta V sub I goes to 0, and this corresponds to our definition of a triple integral. So our triple integral here for our cylindrical region is going to be the triple integral over our region Q. So our region, we're saying Q because we're talking about cylindrical coordinates, of f of x, y, z dv is going to be the integral from theta 1, theta 2, the integral from g1 of theta, g2 of theta, and I'm just setting it up for one particular order of integration. H1 of r and theta, h2 of r and theta, and we're going to express our function in terms of cylindrical coordinates. So we get f of r cosine theta, r sine theta, and z, r, dz, dr, d theta. And this volume element is always going to be dv for cylindrical coordinates. We have an r, a dz, dr, and d theta. The r, dr, d theta comes from our region in the xy plane that we're representing in polar coordinates. And then we're adding the z on here. So this r, dz, dr, d theta, some combination of those things will always be your volume element. And for this particular order of integration, we're saying that theta varies from theta 1 to theta 2. R varies from g1 of theta to g2 of theta. And z is varying from h1 of r and theta to h2 of r and theta. So again, just to reiterate, this outer double integral, the integral theta 1, theta 2, g1 theta, g2 of theta, r, dr, d theta, that outer double integral is our double integral for the region in the xy plane represented in polar coordinates. And then we add this integral with respect to z to get our integral in cylindrical coordinates. And z varies from h1 of r and theta to h2 of r and theta. And so our order of integration here, the way I set it up, is for a radially simple region. This is normally how we're going to set up integrals in cylindrical coordinates. Most often you will set up your order of integration as dz, dr, d theta. So z is varying from some function to some function, and then we have r, dr, d theta for our region in the xy plane. But we could set it up for any order of integration. So just like with triple integrals, we have 6 possible orders of integration. Any permutation of dz, dr, d theta would give us a different order of integration. So questions on our setup here. Usually we pick cylindrical coordinates when our region in the xy plane is easily represented in polar coordinates. That's how we're going to know to pick cylindrical coordinates. And we've done a couple of times where we set up an integral, a triple integral, in rectangular coordinates. We evaluated the first integral with respect to z, and then we changed our double integral to polar coordinates. So that's essentially the same thing as doing our triple integral in cylindrical coordinates. All right, so let's look at a couple of examples of using cylindrical coordinates. When we can use cylindrical coordinates when we can set it up with cylindrical coordinates rather than rectangular coordinates, it often makes our lives way easier. We avoid trig substitution, we avoid messy integrals, and often the integrals become very easy to evaluate. All right. So let's look at this triple integral, or iterated integral. So there's our triple integral in rectangular coordinates. We want to convert this to cylindrical coordinates. So what we're going to do here, what I recommend that you do, is use the limits on your integrals to sketch your region, and then work on converting that to cylindrical coordinates. We want to get an idea of what we're looking at here. So from the limits, our limits of integration always tell us about our limits. Always tell us about our region. So from our limits, we get that for the inner integral, x squared plus y squared is less than or equal to z, less than or equal to 4. For the next integral, we have negative square root of 4 minus x squared, less than or equal to y, less than or equal to square root of 4 minus x squared. And then the outer integral, we have negative 2 less than or equal to x less than or equal to 2. All right, so let's look at, first off, what is this? That's a circle. This tells us that we have x squared plus y squared equals 4. So in the xy plane, we have a circle. And we have the complete circle, not just a half circle, because we have the negative 4 minus x squared to 4 minus x squared. So in the xy plane, this tells us that we are talking about this region. And then this, and that also takes care of this negative 2 is less than or equal to x, less than or equal to 2. X is varying from negative 2 to 2. This are limits on z. X squared plus y squared is less than or equal to z. What is x squared plus y squared equals z? What kind of surface is that? What is it? Paraboloid. We have parabolas in the xz plane and in the yz plane. So this is a paraboloid. So here's my paraboloid. And this limit of integration says that z varies from x squared to y squared to z equals 4. So what is z equals 4? What kind of surface is z equals 4? That's a height. That's a plane at the height z equals 4. So we're going from, z is varying from the paraboloid, x squared plus y squared equals z, up to z equals 4. So we're taking a little cut out like this, and this we're hitting here at z equals 4. So z is varying from the paraboloid up to z equals 4. So So we're ready to set up our integral, our triple integral in spherical coordinates. We have our region in the xy plane that's easily representable in polar coordinates, and we can convert these things to cylindrical coordinates. So let's set this up. And I'm going to write out my integrals, and we'll put our variables on here. Theta is varying from what to what here in this region? 0 to 2 pi. R is varying from what to what in this region, our radius? 0 to 2. And Z is varying from Z equals x squared plus y squared in cylindrical coordinates. R squared. Z is varying from r squared to 4. And then x in cylindrical coordinates is our cosine theta. And then our dv, our volume element, is r dz dr d theta. So our integral would be 0 to 2 pi, triple integral, 0 to 2, r squared to 4, r squared cosine theta, dz dr d theta. Not a particularly difficult integral to evaluate. We're evaluating r squared cosine theta with respect to z. So I just end up with a z in front of here, and I evaluate it between these limits. And the my r integral from 0 to 2, not too bad. And my theta integral, I just have a cosine theta that we end up with in there. So it shouldn't be too bad. But let's look at this integral for a second. We have the integral of x dv. What does the integral of x dv represent? We're multiplying our volume element, dv, by x. So we're taking our volume element and we're weighting it by the distance x. Distance x is the distance from what thing? Not an axis, but from the plane. Which plane? X is the distance from the yz plane. So what is our integral of x dv? It's a moment about the yz plane. So this integral is the moment about the yz plane. So this gives us m of yz, moment about the yz plane. Well, here's the yz plane along here. What do we know about our solid with respect to the yz plane? It's symmetrical about the yz plane. What does the moment about the yz plane evaluate to for a symmetrical shape? 0. This integral represents the moment of this solid about the yz plane. It's symmetrical about the yz plane. So that integral is going to evaluate to 0. There's as much mass on one side of the yz plane as there is on the other side of the yz plane. We could evaluate it and come up with 0. But if we remembered that this is a moment integral, we'd save some work. Kind of nice, huh? All right, questions on our setup. This part I wouldn't necessarily expect anyone to pick out really quickly. But do we have any questions on the setup of the integral? Setup of our triple integral. Okay, let's look at another one. We want the volume of the solid inside x squared plus y squared plus z squared equals 4, and above the upper portion of z squared equals x squared plus y squared. First off, let's figure out what we're talking about here. X squared plus y squared plus z squared equals 4 is what? The sphere. And we want above the upper portion of z squared equals x squared plus y squared. Z squared equals x squared plus y squared is a... In the xz plane, we get z squared equals x squared. So we take the square root of both sides, we get z equals plus or minus x. So this is a cone. So we want the volume inside the sphere above this cone, the upper portion of the cone. So let's try to make a sketch of what we're talking about here. Here's our cone. And here's our sphere. I'll do the sphere in red. So there's the sphere, the sphere in the first octant, and our cone, like so. Let me undo that, do a little better here. So there's our cone. So we want the part that's inside the sphere and above the cone. So the part of the sphere that's inside this cone. So they're going to, the sphere and the cone are going to intersect here, like so. And we want the volume of the sphere that's inside the cone there. So it's kind of like the volume of your ice cream inside your ice cream cone. And we'll do this another way tomorrow. All right. So we need to find this region in the xy plane. So the cone and the sphere are going to intersect, and we're going to project that down into the xy plane, and that's going to give us our region of integration in the xy plane. So the sphere and the cone. The sphere and the cone are going to intersect when I'm going to substitute x squared plus z squared for x squared plus y squared. So 2z squared equals 4. So that's telling me z equals 2. When z equals 2, I get x squared plus y squared equals 2. Let's see. 2z square root of 2, yes. Divided by 2, z squared is square root of 2. So x squared plus y squared is square root of 2. So this is our region in the xy plane. So I'll sketch a quarter of our region. We get x squared. This x squared plus, that's what I wanted. X squared plus y squared equals z equals square root of 2. X squared plus y squared equals 2. Are we good now? X squared plus y squared equals 2. So that's our region in our xy plane. And z is going to vary from the cone to the sphere. So we want the portion that's above the cone, above the cone and inside the sphere. So z is going to vary from the cone to the sphere. On the cone, z equals what? Z squared equals x squared plus y squared. Z equals r. Z squared equals x squared plus y squared. X squared plus y squared is r squared. So z squared equals r squared. So z equals r. So that's the equation of a cone in cylindrical coordinates. Z equals r. On the sphere, z equals, and we're using this equation now, z equals the square root of 4 minus x squared plus y squared, or 4 minus r squared. So now we have our limits for our triple integral. We have our region in the xy plane. We have our function z expressed in terms of r and theta. And now we can put everything into our integral. So the volume is going to equal the integral. Theta is going to vary from what to what on our region? 0 to 2 pi. We have a circle. X squared plus y squared equals 2. 0 to 2 pi. R is going to vary from 0 to, here's our circle. R goes from 0 to square root of 2. The radius of this circle is square root of 2. And z varies from r on the cone to square root of 4 minus r squared on the sphere. And my volume element, r dz, dr, d theta. So there's our volume. And we can evaluate this integral, not a difficult integral to evaluate. Let's go through the evaluation here. So we get the integral from 0 to 2 pi, the integral from 0 to square root of 2. We're evaluating the integral r dz, so we get rz, evaluated on z equals r to the square root of 4 minus r squared, dr d theta. When we evaluate this integral, we get the integral from 0 to 2 pi, the integral from 0 to square root of 2, pi square root of 2, of r, square root of 4 minus r squared, minus r squared, dr d theta. Nice, we end up with a nice u substitution here, and this is a nice easy integral to evaluate. So we end up with integral from 0 to 2 pi of, when we evaluate this, minus 1/3 4 minus r squared to the 3/2 minus r cubed over 3, and we're evaluating that on 0 to square root of 2 d theta. And then when we evaluate this, and our theta integral evaluates just from 0, we end up with a 2 pi in there. This evaluates to 8 pi thirds times 2 minus square root of 2. So nice easy integral to evaluate there. So that would be the volume of our ice cream inside of our cone. for that particular cone and that particular sphere. Questions there? We'll look at the same setup tomorrow in spherical coordinates. All right. All right, there we go.